This is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. So welcome to this lecture. In this lecture, we'll discuss about the common collector configuration of transistor, its VI characteristics, that is the input and output characteristics of common collector configuration. And also we'll discuss the relation between the current amplification factors of the three different configurations of transistor, that is common base, common emitter, common collector configuration. Those are alpha, beta and gamma, and the relation between that current amplification factors, that is alpha, beta and gamma. So first of all, as we all know what is a transistor and what are the three different configurations of a transistor. As we all know that the transistor is a three-terminal device. We can also call it as BJT, bipolar junction device. So, here it is common collector. So, sorry for the mistake. So, common collector configuration. So, here, as it is a three-terminal device, we can connect the transistor in three different configurations by taking one of the three terminals as common between the input and output terminals. And here, like that, we can have three configurations: common base, common emitter and common collector configuration. So in this lecture, we'll discuss about common collector configuration. What is a common collector configuration? So the base terminal of the transistor serves as the input and the emitter terminal is the output, and the collector terminal is the common terminal for both the input and output. That means in the configuration in which the collector terminal is taken as common and the base terminal acts as an input terminal and the emitter terminal acts as output terminal is known as common collector configuration. As a collector is common between both the input and output terminals, we are calling this configuration as common collector configuration. So here, as it is a common collector configuration, we have to remember that the collector terminal is grounded, and hence the common collector configuration is also known as grounded collector configuration. So these are the circuit diagrams which are showing the transistor connected in common collector configuration. So here we have considered NPN transistor, which is connected in common collector configuration. So this is the NPN transistor, which is identified by the direction of this arrow. As this arrow is pointing out, so we have to identify this transistor is NPN transistor. So whereas the base is P type and the emitter and collector are N type. So as it is common collector, the collector is a common, whereas the base terminal is considered to be input and the emitter terminal is considered to be output. That means the input is applied between the base and the collector terminal, whereas the output is taken from emitter and the collector terminal. So here I always tell you that whenever we are using a transistor in any of the configuration, the major application of transistor is for amplification. So always we have to remember that the emitter to base junction should be forward biased and collector to base junction should be reverse biased, such that the transistor operates in the active region. Whenever the transistor operates in active region, it acts as an amplifier. Okay, so here now we are providing the biasing such that the emitter to base junction is forward biased and collector to base junction is reverse biased. So here as emitter to base junction, so that means base terminal should be forward biased. As the base is of P type, so the positive terminal of the supply is connected to the P type base and the negative terminal is connected to the ground, or else we can also say it as to the collector. So positive terminal of the battery is connected to the base and negative terminal is grounded. And similarly, so the collector to base junction should be reverse bias. So that means we need to reverse bias the base terminal. So we need to reverse bias the collector terminal. So what is the type of collector here? As it is NPN, collector is of N type. So in order to reverse bias this collector terminal, So we are connecting the collector terminal to the positive terminal of the battery, which reverse biases the collector junction. So, and the emitter should always be forward biased, right? So, emitter is of N type. So, we are connecting the negative terminal of the battery to the emitter. So, here the VBC, which is the external supply, is connected such that the base terminal is forward biased. Okay, and here the VAC is connected such that the collector terminal is reverse biased and the emitter terminal is forward biased. That means the positive terminal is connected to the N-type collector and negative terminal of the battery is connected to the N-type emitter such that emitter is forward biased and collector is reverse biased. So this is common emitter configuration. And we all know that this is the resistance across which we are going to take the output, that is emitter resistance. And even we do have a resistance here, which is RB, in order to limit the overcurrents. So as the internal resistance are of negligible, so we may also neglect this. So that is why we didn't consider this. But we should have a resistance in order to limit the overcurrents here. So RB will be there. Even if you consider or not consider, doesn't matter, because these are negligible. And here this must be there in order to take the output across the emitter terminal. So base is the input and emitter is the output. We have to remember in common emitter configuration. And the collector terminal is grounded. So this is the transistor. This is the symbol and this is just a transistor in which we are representing the emitter, base and collector with type of materials here. So base is P-type, emitter and collector are N-type. And the biasing is applied such that emitter junction is forward biased and collector junction is reverse biased. So this is the common collector configuration. And as we all know that as it is an NPN transistor, the emitter current will always be coming out, okay, or else leaving. So as emitter current is leaving, as we all know that there is a relation, that is IE is equals to IB plus IC. So as emitter current is leaving, so base and collector current will be entering. So that is here base current and this is collector current. Actually this should be this direction. So this is the collector current. Emitter current is leaving and base and collector currents are entering. So this is what the direction actually. Okay, so base current and collector current are entering while the emitter current is leaving. So these are the conventional current directions which are shown in the common collector configuration. So now let us see what are the characteristics of common collector configuration transistor. So as we all know that in case of common collector configuration, so the common collector configuration is also referred to as emitter follower. Why it is referred to as emitter follower, we'll just see now. And it is also called as voltage follower and also common collector amplifier or else CC amplifier. So this is also called as emitter follower or voltage follower or common collector amplifier and common CC amplifier. So why it is called as emitter follower? Because here in this case, in the case of this common collector amplifier, so whatever the input we apply at the input side to the base terminal, so the same thing will be coming as output at the emitter terminal. So that means the input and output voltages are almost equal. So that is why it is called as voltage follower. That means the output follows the input signal. So whatever the input we apply, we can get the output similar to same as that input signal. So that is why it is called as emitter follower or else voltage follower. And here it is also used as voltage buffer. Buffer means what? It is a temporary storage. As there is no difference between the output voltage and input voltage, so here it is just storing the voltage given. So that is why we can also call it as voltage buffer. The common collector amplifier has high input impedance and low output impedance. So these are the characteristics here. It is having high input impedance and low output impedance, because in the case of output we have what the emitter junction is forward bias, across which we are taking the output, as the emitter junction is forward biased and across the emitter terminal we are taking the output. So here we can say that the output impedance will be very low because it is forward biased. Okay, so as it is forward bias, under forward bias condition, the resistance offered by the diode will be very less. So that is why the output is having very low low output impedance as well as high input impedance. Why? Because so we all know that base current is due to recombination. In the base terminal. Okay, so this recombination will be very less. Why? Because the base is lightly doped. Base is lightly doped. As the base is lightly doped, there are a number of charge carriers that recombine with the holes in the base region will be less, and hence the base current will be very less. As a base terminal is considered as input, as the base current is low, when we can have a less current, when we have more impedance. So that is why we are saying that in common collector amplifier, input impedance is high, whereas the output impedance is low. Input impedance is high because the input is applied to the base terminal, where the base current is very less, and the less current flows only when there exists more impedance. So that is why input impedance is high as well as low output impedance. Why we are getting low output impedance? Because we are taking the output across the emitter terminal, where the emitter terminal is forward biased. Under forward bias condition, the diode offers very low impedance. So that is why the output impedance is low, whereas the input impedance is very high. And it has low voltage gain. As I told you that the output voltage is approximately equals to input voltage. Is there any amplification done? No. So that is why we can say that the voltage gain is very less, whereas the current gain is very high. So that means the common collector amplifier has high input impedance, low output impedance, and it has low voltage gain and high current gain. And the power gain of the common collector amplifier is medium, that is moderate in between common base and common emitter configuration. And the input supply voltage between the base and collector is denoted by VBC. Okay, so what we are doing, we are applying the voltage between the base and collector terminals, so which is represented with VBC, while the output voltage between the emitter and collector, which is represented with VEC. So this is VEC. Why? Because here if you see the circuit diagram, so the collector terminal is at the positive potential, more positive potential, and the emitter is at more negative potential. So instead of using this, we can also have this as VCE also. Okay, because the collector terminal is more positive potential. So as I have told you that whenever we are representing the voltages and currents, so the terminal which is at the higher potential should be represented first, whatever it may be the configuration. So VCE also we can use. And the input current, what is the input terminal in common collector configuration? Base is the input terminal. So IB will be the input current, and the output current, the output is taken across the emitter terminal, and hence IE will be the output current. So what are the output parameters we have? Output parameters are IE and VEC, and the input parameters are IB, because the input is applied to the base terminal and the input voltage is considered to be VBC. So these are the input and output parameters of common collector configuration. Now let us see the characteristic curve. So as we all know that in order to analyze the operation of a transistor, so the three different characteristic curves are input characteristics, output characteristics, and transfer characteristics. So now let us see the input characteristics, output characteristics, and transfer characteristics of transistor under common collector configuration. So first of all, input characteristics. So as we all know that the input characteristics are the graph drawn between the input voltage and input current by taking the output voltage as constant. So whenever we are drawing the input characteristic curve and the input current is taken on y-axis by keeping the output voltage as constant. So here, now that means the input characteristics shows the relationship between the input current, that is the base current in common collector configuration, and the input voltage, which is VBC, that is base to collector voltage in common collector configuration. So first of all, to determine the input characteristic curve, the output voltage, what is the output voltage is in common collector configuration? VEC is the output voltage. So keep the VEC, that is the output voltage, as constant and increase the input voltage in steps and record the value of input current IB, and then draw the graph between VBC and IB by taking VBC on x-axis and IB on y-axis. And one thing we have to remember, as IB is a recombination current which takes place in the base region. So as the base region is lightly doped, so the number of charge carriers, that is majority charge carriers present in base region, are very less, and hence the rest amount of recombination takes place, and hence the base current will be very less, and the base current will be of the order of microampere. So that is what we have represented on the y-axis, IB in microamperes, whereas VBC in volts. So now, first of all, keep the output voltage as constant at some 0, and then increase the voltage, input voltage in steps, and record the values of input current, and then plot the graph between input voltage and input current. So here, now what happens? So these are the characteristic curve. So why we are getting like this? So we have to remember that we have an effect called early effect or else base width modulation. So what happens due to that early effect or base width modulation? So for example, let us consider this is an NPN transistor. Okay. So here this is the base region, emitter region, and this is the base, and this is the collector region. This is of N type, this is of P type, and this is of N type again. So now what happens here? Whenever, always you remember, this emitter to base junction is forward biased, emitter junction is always forward biased, and collector junction is always reverse biased. So here now, whenever VEC, what do you mean by VEC? This is the voltage drop, voltage between the collector and emitter terminal. If I increase VEC, the reverse voltage at the collector junction will also increase, due to which what happens, the depletion region will penetrate more into the base region, less into the collector region, because the base is lightly doped, and hence the width of the depletion region in the lightly doped semiconducting material will be very high. And hence here what is happening, whenever we increase VEC, so there will be more depletion region penetration into the base when compared to the collector region. And now what happens? So here, now as we are increasing VBC, so the reverse voltage across the base to collector junction will be increased. So what I said, first we need to keep VEC at constant, that is for example 3 volts let us consider. So after keeping that VEC at constant, we have to increase VBC in steps. As we are going on increasing the VBC, so the depletion region will be increasing, the width of the depletion region will be increasing, and due to that, the effective width of the base region where the recombination takes place will be reduced, and hence finally what happens, the base current will be reduced. So this is due to the early effect. That is what do you mean by early effect? The variation of width of the base region where the recombination takes place, the reverse voltage applied to the collector junction will be increasing, due to which the effective width of the base region where the recombination takes place will be reduced. Due to that, what happens? The amount of recombination will be reduced, due to which the base current will be reduced. So that means initially the base current will be high, and as the base to collector voltage VBC is increasing, the base current will be reduced. So that is why initially it is starting from high value and it is going on decreasing. At one point of VBC, the base current will be reduced to 0. So this is the curve we are getting like this. So whereas when we compare this one with the common emitter and common collector, initially the current was 0. Once the input voltage exceeds the cut-in voltage, the conduction takes place, conduction starts, and hence the current will be increasing. But here initially the IB current will be more. As we are going on increasing VBC, due to the early effect, the base current will be reduced due to the reason that the effective width of the base will be reduced, and hence the recombination rate will be reduced, which further reduces the base current. So that is why as the VBC is increasing, the base current is reducing. So this is the characteristic curve of common collector, input characteristic curve of common collector configuration transistor. So initially base current will be high. As VBC is increased in steps, the base current is decreased. Okay. So now this is when we keep VEC at 3 volts. Now if I increase VEC to some other value, let us consider VEC is equals to 5. What do you mean by VEC? This VEC, if you observe that circuit diagram which I have shown earlier, so if you increase VEC, which also increases the reverse potential applied to the collector junction. Is it clear? So VEC also makes the collector junction reverse bias. So as I increase VEC, the amount of reverse voltage applied to the collector to base junction will be increased. Due to which, what happens? The more the junction, that is the collector junction, is more reverse biased, and hence the width of the depletion region again increased, and hence there will be early effect, that is the base width modulation arises, due to which the effective width of the base region will be reduced, and hence which in turn increases the emitter current, and hence the input voltage will also be increased. So means what? That means at higher potential the conduction the conduction takes place, and hence that means initially the conduction was started at some lower potential. Due to the increment in the VEC, that is the reverse voltage at the emitter to collector junction. So here what happens? The conduction takes place at more higher voltages, and hence the curves will be shifting towards the right side, or else moving away from the origin as we are increasing the output voltage VEC. So that means if we increase VEC, due to again the same early effect, the characteristic curves are moving towards the right side. So that is why we are getting the same thing, and again the same thing happens. So as we are going on increasing, once the conduction has started, as we are going on increasing this VBC, which increases the reverse potential at the collector to base junction, which in turn reduces the base current. So this is what the characteristic curve of common collector configuration. So this is about the input characteristics of common collector configuration. Now let us see the output characteristics of common collector configuration. So as we all know that the output characteristics is a curve which is showing the relationship between the output voltage and the output current by taking the input current as constant. So what is the output voltage in case of common collector configuration? That is VEC. That means the output characteristics of common collector configuration shows the relation between the output voltage, that is VEC, and the output current IE by taking input current, which is IB, as constant. IB is constant here. Okay. So now to determine what we need to do to determine the output characteristics, first keep the input current IB at some constant value. Initially we will be keeping the IB at 0 as constant. That means open circuiting the input, and recording the values of output current by changing the output voltage in steps, and drawing the graph between output voltage, taking the output voltage VEC on x-axis and output current IE on y-axis. So we can draw the characteristic curve here. So here initially we need to keep IB as 0. Making IB 0 means we are open circuiting the input port. That means input junction means what? Both the junctions, and already we are providing the biasing such that output junction is reverse biased. By making IB is equals to 0, the input junction is also reverse biased, and hence it is said to operate in cutoff region. As both of the junctions are reverse biased, so it acts as it works in cutoff region. These are the output characteristics of common collector configuration. So here these are similar to the output characteristics of common emitter only, but only the difference is we are taking the VEC on x-axis and IE on y-axis here. So here, why I'm saying that these characteristics are similar to common emitter configuration, because IE is equals to IB plus IC, we all know that, whereas IB is very negligible. IB is very negligible, right? So if IB is negligible, so what happens? We can say that IE is approximately equals to IC. So where in case of common emitter configuration, what are the characteristics? Emitter is common, right? Emitter is common, and base is the input terminal and collector is the output terminal, right? So in that case, what are the output parameters? The output parameters are IC and VCE. IC and VCE. So where here in this case, IC is approximately equals to IE, right? So here the output characteristics are drawn for the common collector configuration between IE and VCE, whereas the output characteristics are drawn for common emitter configuration between IC and VCE, where IE and IC are approximately equal. So, and hence we can say that the output characteristics of common emitter configuration are similar to the output characteristics of common collector configuration. So, these are the characteristics of common collector configuration which are similar to the common emitter configuration. This is the reason why these are identical to the common emitter configuration. So, as we all know that when IB is equals to 0, so in both the cases, what we are doing, the input current is base current, right? In common emitter also, base current is input current, and in common collector also, base current is the input current. So that means both are same, the output parameters are almost same, and even the input current is same. That means the characteristics are similar to common emitter configuration. So if IB is equals to 0, so what happens? Both the junctions will be reverse bias, and hence as both the junctions are reverse bias, the region of operation is said to be cutoff region. So this region is said to be cutoff region, and in this region we have almost the output current is equals to input current. So we can say that in this region the emitter junction is forward biased and collector junction is reverse biased, and hence this region of operation is said to be active region. And now coming to this region, this is said to be saturation region, because this is positive voltage which is applied to VEC, whereas we are applying a negative voltage which forward biases the output junction. Already by applying some current, what we are doing, we are forward biasing the base junction. Now by applying the reverse voltage, that is negative voltage to VCE, so we are also forward biasing the collector to base junction. That means in this region, both the junctions are forward biased, and hence the transistor operates in saturation region. So in saturation region, transistor acts as on switch, and in cutoff region, transistor acts as off switch, and in active region, it acts as amplifier. So these are the output characteristics of common collector configuration which are similar to the common emitter configuration, right? Now let us see the transfer characteristics of common collector configuration. So these are the transfer characteristics of common collector configuration. Anyhow, whenever we are making the input current IB, so the output current is IE, right? So here, whenever the input current is 0, there will be some leakage current flowing, and that is why we are showing that starting from some leakage current here. So this is, and after this, when IB increases, the IE also increases. So this is the transfer characteristic curve of common collector configuration, which shows the relation between the input current IB and the output current IE of a transistor under common collector configuration. And from this characteristic curve, we can define a parameter which is known as current amplification factor or else current gain, which is defined as the ratio of change in emitter current, change in emitter current to the change in base current, because it is the gain. Gain is always defined as a ratio of output to the input. So the output current is IE and the input current is IB. So gamma is the current amplification factor in common collector configuration, where it is defined as a ratio of change in emitter current to the change in base current. And it is denoted by gamma. And here we all know that IB is very less of the order of microamperes, where IE is milliamperes. So as the denominator is a less value, so the amplification factor, that is gamma, will be very high, because the denominator is very less, which is of the order of microamperes. So that is why the current gain or else current amplification factor of common collector configuration or else common collector amplifier is high. So now coming to from the input characteristic curve, we can define one more parameter, which is nothing but dynamic input resistance. So all the dynamic characteristics are defined with smaller letter, represented with smaller letters. So small Ri. And a dynamic input resistance is defined as a ratio of a change in input voltage. What is the input voltage in common collector configuration? BBC, that is collector to base voltage. And with respect to the change in input current, IB, by keeping the output voltage VEC as constant. So RA is equals to delta VBC by delta IB by keeping VEC as constant. So again in this ratio, IB is very less. It is of the order of microamperes. So that means input impedance is very high. So that means we have to identify that the current amplification factor is high and even the input resistance of the common collector amplifier is also very high. Now coming to the output characteristic, dynamic resistance, output dynamic resistance, so which can be calculated from the output characteristic curve of common collector configuration. So resistance is always defined as a ratio of voltage to the current. So as we are measuring the output resistance, so the dynamic output resistance is defined as a ratio of change in output voltage, that is VEC, with respect to the change in output current, that is IE, by keeping the input current as constant, which is IB. So that means that is defined as a ratio of VEC, change in VEC with respect to the change in IE by keeping IB as constant. So it is R naught is equals to delta VEC by delta IE at IB as constant. So IE, what is IE? It is actually milliamperes. It is of the order of milliamperes. So that means here the denominator is high when compared to the numerator, and hence we can see that R naught value will be very low. So that means the common collector amplifier, the output impedance is very low, whereas the input impedance is high and the current gain is also high. So these are the various characteristic parameters that we can calculate from the characteristic curves of this common collector configuration. So one thing you have to remember, so the current gain is calculated from the transfer characteristic curve, input impedance is calculated from the input characteristic curve, output impedance is calculated from the output characteristic curve. Now let us have a discussion on the current components in the common collector configuration. So IC is equals to alpha into IE plus IC B naught. This is, we know, this is from the common base configuration. Okay, common base configuration of transistor. So that is IC is equals to alpha into IE plus IC B naught, where alpha is the amplification factor of common base configuration, IE is the input current, IC is the output current, where IC B naught is the reverse saturation current, or else we can also call it as leakage current. And we all know that there is a current relationship, that is IE is equals to IB plus IC, and this holds good for all the three configuration and also two types of transistor. That means this equation is valid for NPN or PNP transistor, and also it is applicable for all the three configurations of transistor. So IE is equals to IB plus IC. Now here, what is the in common collector configuration, input current is what? IB, whereas output current is what? IE. That means I have to express IE in terms of IB. In terms of IB. Okay, so what do we have? We have a relation between IC and IE, and we have a relation between all the three currents. Now I want to get a relation between IE and IB. That means I want to express IE in terms of IB here. So now for that, IB, so in place of IC, we are substituting this equation. So alpha into IE plus ICB naught. So now take this IE term this side. So if I take this term this side, IE minus alpha into IE is equals to IB plus ICB naught. Right? Now let us take IE as common in these two. Then I'll get IE into 1 minus alpha plus IB plus is equals to IB plus ICB naught. Now send this term this side. Then I'll get IE is equals to IB by 1 minus alpha plus ICB naught by 1 minus alpha. So now here what I'm considering, see here we all know that beta is equals to alpha by 1 minus alpha. So here if you consider beta plus 1, so what happens? Alpha by 1 minus alpha plus 1. So take LCM here, 1 minus alpha. So alpha plus 1 minus alpha. So alpha get cancelled. So that is 1 by 1 minus alpha. That means what I can say, beta plus 1 is equals to 1 by 1 minus alpha. So that is why I am replacing this 1 by 1 minus alpha by beta plus 1. So IC is equals to approximately equal to IE. So IC is approximately equals to IE, which is equals to beta plus 1 into IB plus beta plus 1 into ICB naught. So this is the relation between the emitter current and the base current. So beta plus 1 into IB plus beta plus 1 into ICB naught. So this is the equation. So I can write this equation, IE is equals to gamma into IB plus gamma into ICB naught. So this is the relation where it is showing the relation between IE and IB. So here from this I can say that gamma is equals to 1 plus beta. So now we can have a relation between all the three current amplification factors, that is alpha, beta and gamma. What is alpha? Alpha is the current amplification factor of common base, beta is the current amplification factor of common emitter, and gamma is the current amplification factor of common collector. As we all know that alpha is equals to beta is equals to alpha by 1 minus alpha. And similarly, we can have a relation between beta and gamma. So gamma is equals to 1 plus beta. And also we can have a relation between alpha and gamma. So gamma is equals to 1 by 1 minus alpha. 1 by 1 minus alpha. So here that means we can say that gamma is equals to 1 plus beta, or that also is equals to 1 by 1 minus alpha. So this is the relation between all the three current amplification factors, that is alpha, beta and gamma, which will be very important, which is a very important relation with showing the relation between all the three current amplification factors, alpha, beta and gamma. And based on this, we will also solve some of the problems. So we have to remember all these current equations. So now let us have a look of all the current equations here. First of all, in common base configuration, IC is equals to alpha into IE plus ICB naught. And we can also have, this is for the common base configuration. And we can also have IC is equals to beta into IB plus ICE naught. Okay, ICE naught, this is for common emitter configuration, where ICE naught is equals to beta plus 1 into ICB naught. This we have to remember. These two are for common emitter configuration. And now for common collector configuration, IE is equals to gamma into IB plus gamma into ICB naught. So these are all the three relations that we need to remember, and also these relations we have to remember for solving some numericals on the transistor current components. So this is about the current components in common collector configurations. Okay, so where we compare with this alpha is very less when compared to beta and gamma. Okay, So here gamma is also very high, because we have seen already gamma is a current amplification factor of common collector configuration. It is also very high. So now let us have a look about the comparison between the three configurations of transistor, that is common emitter, common base and common collector. This is a table which is showing the comparison between the three configurations: common emitter, common base and common collector. And these are the parameters by which we are comparing the three configurations. So first of all, input resistance. In common emitter configuration, input resistance is very low, and it is of the order of 1 kilo ohm to 2 kilo ohms. Whereas for common base, input resistance is very low. It is of the order of 30 to 150 ohms, whereas it is kilo ohms, whereas it is ohms. So that is for common base configuration, the input resistance is very low. Whereas for common collector configuration, input resistance is very high. It is of the order of 20 to 500 kilo ohms. And coming to the output resistance, it is large for common emitter configuration, and it is approximately equals to 50 kilo ohms. For common base configuration, it is high. It is of the order of 500 kilometers, and it is low for the common collector configuration. It is varying from 50 to 1000 kilo ohms. And now coming to the current gain. Current gain is high for common emitter configuration, that is beta. Beta is high for common base configuration, whereas alpha is a current amplification factor or gain for common base configuration, which is less than 1. And it is also high for common collector, that is given by 1 plus beta. And now coming to the voltage gain, it is high in common emitter configuration. It is up to 1500. And common base also it is high, 1500, and it is less than 1 in case of common collector. That is why we are going to use this as voltage buffer. Voltage buffer. That means in this case the output voltage is approximately equals to input voltage. So that is why we are going to use this common collector configuration as buffer. Okay. And power gain, it is high. It is of the order of 10,000 for common emitter. And for common common base, it is also high. It is the ideal value for common power gain is 7,500, and it is low of the order of 250 to 500. This is the power gain for common collector configuration. And the phase between the output and input. So here, always you remember, in common emitter configuration, the output is phase reversed by 180 degree when compared with the input signal. There is a phase reversal of 180 degree between the input and output. That means if the input is positive, the output is considered to be negative. So that is reverse. That means there is a phase difference of 180 degree. Whereas the output and input in case of common base and common collector configuration are in same phase. That means in phase. There is no phase difference between the input and output in both common base and common collector configuration. So these are the differences, or else a comparison between the various characteristics of transistor under three different configuration, that is common base, common emitter and common collector configuration of a transistor. So in this lecture, we have seen the common collector configuration, and we have seen the input, output and transfer characteristics of common collector configuration, and the various characteristic parameters of common collector configuration. And we have also seen the relation between alpha, beta and gamma. And we have seen the current equations of all the three configurations, that is common base, common collector and common emitter. And we have finally compared the three different configurations of transistor with respect to various characteristic parameters like voltage gain, current gain, input resistance, output resistance, power gain and all. So I hope this is clear to you. That's all for this lecture. Thank you one and all.
Like, share and subscribe. Hit the bell icon for more updates.